Hello everyone. I have the pleasure to present to you our recent work on private adaptations of large language models. This talk is based on our recent two papers from NeurIPS conference from this and last year. Nowadays, large language models perform a plethora of language tasks. OpenAI exposes its GPT-4 model to perform tasks such as text translation, text summarization, and so on and so forth. And here is a simple example that we just ask the ChatGPT to recite the first law of robotics. OpenAI's codex system translates natural language to code. So you can type a command in the text box on the left-hand side and then see the corresponding code on the right-hand side. LLMs like Gemini can be used to verify solutions to physics problems. So here is an example that the model can recognize handwritten content, and the text, actually the solution to the problem, is incorrect. And the student used incorrectly variable L instead of variable H. Behind the scenes, the creation of LLMs that underpin such ML APIs is a costly venture. There are three main factors that contribute to this high cost. First, it is hard to collect and clean large amount of data. Second, we have to hire ML experts to tune hyperparameters for these models. And finally, expensive hardware such as GPUs, TPUs, or many CPUs are needed for both training and inference. For example, it was estimated that a single training round of GPT-3 model costs north of $12 million. Unfortunately, most of us cannot afford training such LLMs from scratch. So the question is, how can we adapt such LLMs to our own needs? The adaptations of LLMs can be done in a plethora of ways. I'll present three main ones. Currently, the most popular way is through prompting, denoted as 1 in this figure. The input prompt can be discrete, where you prepend additional natural language text to your standard input. Soft prompts are a learnable set of parameters that are prepended to the input embeddings. And prefix, also called prefix tuning, is similar to soft prompt, but apart from being prepended to the input, it can also be prepended to every attention layer. This is probably the most known version of prompts. The second approach to adapt LLMs is through inner fine-tuning. You can do it either through full fine-tuning, where you adjust all the parameters of your LLM, or using low-rank adaptations, abbreviated as LoRA. So here for LoRA, a small set of additional parameters is added within the main layers of LLM. Finally, we can fine-tune a couple of last layers of LLMs, or even add an additional layer on top of the LLM, and this is called output or last layer fine-tuning. So what are the main differences between these methods, especially prompting versus fine-tuning? So prompt tuning only requires storing a small task-specific prompt for each task, and then enables multitask inference using the original pre-trained model. We need to store only a small prompt per task with around 10k parameters. Most importantly, in a single batch, we can include prompts for many tasks and even for different users. On the other hand, for fine-tuning, it requires us to store a separate copy of the model per task. So this, of course, is costly in terms of storage, but also computation, because we cannot just bunch different tasks for a given LLM. Now we'll focus on prompting. Let us start from the simple case of discrete prompts. They usually consist of two parts, namely an instruction that tells the model what to do with the input, and the private demonstrations, also called shots. They provide an example of how to solve a given task at hand. If we, for example, want to use an LLM to recognize whether the sentiment of a movie review is positive or negative, a discrete prompt could look like the one on the green background, this prompt template. We tell the model to classify the movie review and give the model examples on how to do it. And then learning such discrete prompts does not use any propagation of the gradient. Instead, we sample multiple examples. Also, we have to find out what is the best instructions. we usually generate many of these different discrete prompts and then evaluate which of them is really the best on a given validation set. And then based on this validation, we can choose the prompt that actually yields the best performance. Then when a new example comes, so a new movie review from a given user, for example, here the movie reviews is the movie was great, and then we expect from the model to give the answer being what is the sentiment of this movie review. So here the model correctly classifies that the sentiment of the new movie reviews is positive. Once we started this research about adaptations of LLMs, little was really known about privacy implications of prompts. So in our research, we instantiated the first membership inference attack against a prompted GPT-3 model. Our membership inference attack asks the following but simple question. Given a data point and the prompted LLM, was this data point used as an example in the LLM prompt? The answer to the question is through so-called membership inference attack. So we rely on these techniques from prior membership inference attacks works, and we compare the model confidence on the true output label between member data points, meaning the data points used as examples in the prompt, and non-member data points, which are not data points used in the prompt. The intuition is that if a model has seen an example in the prompt, so the prompt contains the given demonstrations from this our tested set, then the confidence of the model on these samples is much higher than when the model is queried with the unseen examples, so the examples that are not actually included in the private demonstrations in this prompt template. And here, since we operate with generative models, we take the tokens that the class labels belong to, for example, positive or negative, and then these tokens are basically our classes for the given, in this case, movie review. What we observe is that there is a significant privacy risk for the data points used as examples in the prompt. So simply, these examples that are included in the private demonstrations can be easily found out if we have access to this prompted LLM. Adversary might go even a step further and attempt to directly extract the private demonstrations or shots. This is also called a jailbreak, where one tries to fool the model, where instead of fulfilling the given task, it extracts the private data from the prompt. If the private demonstrations are data from clinical reports, then this is a severe privacy violation. So here we would like to give a bit more examples of how this membership inference attack works. So this is just to quantify how much really of this privacy leakage can we incur from the given prompted LLM. So we carried our experiments on the GPT-3 model, prompted with examples from DBpedia. So a dataset that classifies the topic of Wikipedia articles. The left figure confirms our hypothesis that the prompted LLM is significantly more confident on the member data points than on non-members. The right figure is the standard AUC ROC curve for our membership inference attack, which shows how well the model can tell apart the member and non-member data points. The further apart the blue curve is from the diagonal, the red line, the red dashed line, the more effective the membership inference attack is. So looking at this result, we see that there is a significant privacy risk for the data points used as examples in prompts. And here we report that the average AUC score for this attack is 0.84, which is a substantially high score. So these results highlight that private information can leak from prompt data easily, and this also motivates the urgent need to provide defenses, which we also develop in our work. So we show that this privacy leakage is happening for discrete prompts. Now the question is, does it also happen for other types of adaptations of LLMs? So here we also provide explanation of other adaptations of LLMs, for example, soft prompt tuning or prefix tuning. So here we briefly explain the other adaptation being, in this case, soft prompt. So soft prompt basically can be thought of as a learnable set of parameters prepended to the input embeddings. So here you are given the example of a patient who has a heart pain. The task of the prompt is to classify the patient as being healthy or not. The words from the user's input are tokenized, and each token receives an embedding. Here we embed the token heart and the next token pain. This is prepended with the special token for classification tasks. In the embedding space, once we have the embedding for the classification and the tokens heart pain, we also add the additional embedding for the soft prompt. So the number of tokens embeddings that we add for the soft prompt usually corresponds from 1 to even 100 tokens. It really depends on the task difficulty. If the task is more difficult, then usually actually we prepend more of these additional tokens in the form of these additional parameters for soft prompt. Similarly to soft prompt tuning, you can also do prefix tuning. So prefix tuning, apart from being prepended to the input, it can also be prepended to every attention layer in the LLM. So in principle, prefix further extends the number of parameters that actually can be used for solving a given downstream task. And here we want to train the soft prompt to give us a sentiment of a given patient state. For a patient's input text, heart pain, we append the soft prompt and the classification token. The text is transformed to the input tokens and then embeddings. After the forward pass, we compute the class label with a linear layer head and perform the standard optimization, but instead of modifying LLM parameters, we update the soft prompt parameters. So here the parameters for the LLM are frozen. Note that each embedding is usually with 768 parameters, and the soft prompt itself can consist of one or more token embeddings. The length of the soft prompt is limited by the context size. If this is not enough, then we can also use prefix to further increase the number of parameters that we want to use to solve the given downstream task. However, soft prompts require gradients to train them. This limits us to use this method only for open LLMs, where we have direct access to the LLM's weights. So we use membership inference attack also for these gradient-based adaptations for LLMs. So these adaptations like soft prompt or prefix, or also LoRa, or full fine-tuning. So these adaptations can be carried out for the open LLMs. So here for this task, we adapted PIFIA 1 billion model. So PIFIA comes from this famous suite of models that is open source. So we not only have access to the model parameters, the weights, but we also know what is exactly the training set of the models and how the models were trained. The results are reported here as the AUC score for the latest robust MIA attack. So here in our experiments, we wanted to leverage the strongest membership tag to be able to identify what are the trends. And what was very interesting for us is that we observed that the more the adaptation set is similar to the underlying distribution of the pre-training data, the higher the privacy leakage. And also the same trend was shown for the other adaptations like LoRa or full fine-tuning. So on average, the closer the given adaptation set is to the pre-training set, the more this adaptation data can leak to the querying party. These results highlight that private information can leak from adaptation data easily, and then this motivates the need for defenses which we developed in our research. While previously differential privacy was used to support the head fine-tuning or full fine-tuning as well as LoRa, we propose how to provide private prompt learning for LLMs. So first we show how to do it for discrete prompts, and then we also show how to do it for the soft prompt or prefix tuning. So before we delve deeply into how to prevent the privacy leakage from prompts, I have to introduce a concept of differential privacy. So here, in the context of LLMs, we have in short this differential privacy defined as a mathematical framework to implement formal privacy guarantees. So intuitively, the outputs from this adaptation of LLMs should be the same or indistinguishable, independently of whether or not a given data point is used to learn a prompt or not. So here we consider neighboring prompts, D and D prime, that differ only by a single data point. Let's analyze this main inequality for differential privacy. The parameter epsilon is the most important privacy parameter that determines how close the outputs of the model should be, despite the model being trained on dataset D and D prime that differ only by a single data point. The S is a set of possible outputs. The delta parameter is the probability of a failure, and the data parameter can also be thought about as similarly to the concept in the cryptography, where there is some small probability that adversary, for example, might guess our private key. To implement Pate, so Pate is also like a very famous framework to provide differential privacy for machine learning models. It's one of the two canonical algorithms. We have Pate as well as the PhD, and for these prompts to learn with privacy, we actually leverage both of these frameworks. But here first I will focus on the Pate framework and how we basically use this framework for the discrete prompts. So we start with our private labeled data. We divide this data into many subsets to form prompts. So each prompt contains a disjoint set of examples or shots from the private labeled data. So these private labeled data, they are basically injected into our prompt templates. So now this disjoint subset from the private labeled data are used to create the demonstrations for private teacher prompts. The data serves as private shots. So this blue rectangle represents our prompt template with an instruction saying what kind of task we want to solve, and here the green rectangle inside is some example with potential label. So once we have these teacher prompts, then we use enabled public data to query the LLM with the private teacher prompts. So the private teachers, they are used to label this public data. So how do we do that? So here, to go step by step, we have some enabled public data. The data can come from some public repository of the data, and then for each of these examples we want to find out what is the really correct label. So for the given example, here noted as the blue rectangle, it goes through these teacher prompts and then also through the LLM. So this example is given as the one to be reasoned about, to be labeled by every single teacher. So teacher uses its instruction and examples to label this new public data point, and then each vote from the teacher is collected into this histogram. So here histogram contains, in this case, two classes, positive and negative. We just collect these votes and then aggregate them into this histogram to have vote counts per each single class. Once we have this histogram with the vote counts, we add the Gaussian noise on top of the histogram votes. And this is done to prevent the party who sees this final output, the final label, from inferring which data points actually were used to create these private teacher prompts. Finally, these privately labeled teacher examples are returned to prepare a so-called student prompt. We choose these labeled examples that give us the highest accuracy on the privately labeled public dataset. The innovation in this Pate framework for prompts is that we don't train a new model from scratch, but we leverage this aspect of having LLMs, and we create a new prompt. So we don't have to train anything from scratch. We just choose what are really the best public data points that we actually could include in these shots for the new public student prompt. We analyze the performance of prompt Pate for the DBpedia dataset using GPT-3 model. So the DBpedia dataset is used for text classification. So given article, its title and content, we have to classify what's the article type. And we observe that for the zero-shot prompt, so a prompt with instruction only and without an example or shot, the performance is very low, of around 44.2%. If we analyze on the teacher ensemble, so without any privacy, the performance is almost doubled to 81.6%, and this is because of providing the shots in our prompts. However, our prompt Pate provides us with the best of both worlds. We have high performance of 80.3%, and also very strong privacy guarantee with epsilon less than 0.2. For the another task, so up to now we talked about only text classification, but what about text generation tasks? So to be able to also run Pate with the generation tasks, we had to extend this framework. So to do that, actually, we apply some methods from another framework called DPICL, and we provide this private aggregation for text generation. And this is, in the simple words, based on the idea of a bag of words model. This is one of the simplest model in language domain, where we have to just classify, for example, a given text based on the frequency of the words. So let me focus on this component in red, and then we can explain how we can adjust this framework to the generation tasks. For example, tasks such as dialogue summarization, where given a dialogue, you have to just summarize this dialogue in natural language text. So the private aggregation for text generation is done according to the aggregation proposed in either framework or DPICL. So we decompose all output sentences into individual words. Then we form a histogram based on the word frequencies and also remove the non-meaningful words. So then we employ the exponential mechanism to privately select the keywords. And finally, we construct the final output sentences by using the selected keywords in the prompt and recording the API. If we combine the prompt-pate method with the DPICL, we can increase the performance. Here presented for a dialogue summarization task called Samsung. So the Rouge metric is the recall-oriented understudy for gisting evaluation, but basically what it does is to basically assess how many word-wise n-grams match between the predicted and target text. So we see that in all of these metrics, our prompt-pate outperforms the previous method. And this is primarily because we don't answer just the queries, but we answer the queries to train the student model. Okay. So up to now we described how to provide privacy for discrete prompts, and now we will move on to the soft prompts. So this is the standard SGD algorithm. To start from the beginning, we have as input soft prompt parameters theta, loss function L, and learning rate eta. We consider t-training rounds. We start from the selecting of the data point x sub I for the given iteration. We compute a gradient for this data point, and finally we take a step in the opposite direction to the gradient. To obtain a canonical algorithm to train models with privacy, this algorithm is called DPHD, we have to add only 2 red lines of code. So we add these also additional parameters, being sigma, that determines how much noise for privacy we add, and norm bound C, which is the norm for clipping the gradient. We do not want a gradient from a single example to exert too much influence on the trained model, so we clip it. This is similar to gradient clipping to tackle the problem of gradient explosion, and then we add noise to protect privacy. The random noise added to gradients prevents the final model outcome from reflecting the gradients of any individual data point to protect privacy. How do we incorporate DPHD into the training of soft prompts? We start from our initial parameters for soft prompt embedding. We also have our private data with labels. We provide example like the heart pain and embed this example. The embeddings are prepended with our soft prompt embeddings. The embeddings with prepended soft prompts go as input to the LLM. Based on the expected labels, we can compute the loss and provide gradients for our soft prompts. To make sure that the gradients do not leak information about our private data, we clip the gradient and add noise. Thus, prompt DPHD obtains the input gradients from the LLM and performs DPHD to update the soft prompt embedding while keeping the underlying LLM frozen. What we observe is that for the standard NLP datasets like SST2 for movie reviews sentiment analysis, the performance of the soft prompt is even higher than for full fine-tuning, where soft prompts have less than 10,000 parameters, while fine-tuning was done on a whole LLM here with 125 million parameters, since we used actually Roberta base model. And for this experiment, actually, we use epsilon value equals 8 just to keep the same value as for the other methods proposed for the adaptations of LLMs. For a slightly more difficult dataset of QNLI, which is a standard dataset used for the classification, and this is dataset from Stanford for a question answering natural language inference. So here the task is to determine whether the context sentence contains the answer to the given question. So this is a slightly more difficult dataset than SST2 in terms of like performing classification, and the performance of soft prompt matches the performance of fine-tuning, but in this case we can use also prefix to outperform the full fine-tuning. We also run prefix tuning for the text generation tasks, where the task here is to summarize a dialogue. So despite that this is quite a difficult task, our prefix tuning performs relatively well, despite using much fewer parameters than, for example, full fine-tuning. So up to now, we've showed how to privately tune prompt-based adaptations. Previous work also showed how to adapt LoRa with DP, or also how to use DP for full fine-tuning. So now our next step is to analyze these different methods, especially in the context of how they perform on open versus closed LLMs. The examples of open source LLMs include the PyThia suite of models and Olmo. So these models not only expose parameters, the weights of these models, but also the training sets as well as the code that was used to train the models. We also have open weight LLMs such as Llama or Vicuna. On the other hand, the examples of closed LLMs, so LLMs that are usually exposed through APIs, are GPT, Claude from Anthropic, or Gemini from Google. The open LLMs have to be run on-premise on our own hardware or in the cloud. On the other hand, closed LLMs are usually exposed by model providers via APIs, but also, for example, through web interfaces, where you can directly access them and query them. So while all adaptations can be applied to open LLMs, the closed LLMs can be adapted only through the discrete prompts. So now let us imagine that there is a company, a data curator, and then this company hosts private data locally on-premise on their own hardware. The data curator adapts an OpenLLM on their own private data. So this LLM is adapted so that we can answer some queries about this data. For example, this data curator can be a hospital with patients' data, and then for the new patients that comes, which has a new form of query to the doctor, we could just direct this patient to this OpenLLM, and then given, for example, the symptoms of the new patient, the LLM could answer what are the potential diseases that the patient might have. And then the data curator exposes this adapted OpenLLM through API. A customer comes and they can query this adapted OpenLLM. However, the querying party might be malicious, and in this case, the private information from the data curator can leak to the querying party through the returned answers of the prompted LLM. Now let us look at the case when the data curator does not have any OpenLLM on-premise and would like to use a closed LLM from a model provider. First, the closed LLM has to be adapted to a given private data. So this can be done, for example, through discrete prompts. However, the private data in this case is released to the LLM provider. Second, the private queries have to be routed through the LLM provider, thus again leaking to the third party. Finally, the answers returned to the querying party can leak information contained in the private data hosted by the data curator. Overall, this conceptual analysis shows that the privacy leakage is much higher when adapting closed LLMs versus open LLMs. PromptPate was designed for closed LLMs and prevents the leakage of the private data to the querying party. However, for PROM-PATE, the private data and queries leak to the LLM provider. On the other hand, PROM-DPHD applied to the open LLMs prevents all three types of privacy leakage. Overall, we analyzed 4 recent methods to adapt closed LLMs, including our PROM-PATE. All of these methods were designed for closed LLMs to prevent the leakage of the private data to the querying party. All of them fulfill this goal. However, they leak private data and queries to the LLM provider. The only method that does not leak private data to the LLM provider is DPOPT. However, DPOPT requires the data curator to use an open LLM locally on premise. Most importantly, if we privately adapt open LLMs, only then we can prevent these 3 types of leakage. We carried out an in-depth comparison of the adaptations of open versus closed LLMs, considering the following 3 axes. So first, privacy protection. We want to see which of these methods leak what kind of information, either private data from the data curator or the user queries, or maybe the private data to the querying party, to the user. Also performance, so what is the downstream task performance, either accuracy or some other metrics like blue score or the other scores for the generation tasks, and also cost, so how much really it costs to adapt the given LLM with privacy. So we observed that the adaptations of open LLMs offer higher privacy protection and higher performance at a much lower cost than compared to the closed LLM adaptations. So here, the prompt-based adaptations for closed LLMs offer lower privacy, lower performance at a higher cost compared to their open counterparts. So let us show more these results. We assess the private adaptations using epsilon equals 8, following the previous work, and also 10,000 queries. We show the performance on 4 standard classification tasks. SST2 and MPQA are 2 class sentiment analysis datasets. TREC is a 6-class question type classification dataset. The disaster dataset involves to determine whether a sentence is relevant to a disaster scenario or not. We measure the accuracy and cost for tuning and executing queries for these tasks. So we present the strongest setup for a given method. The PICL is one of the latest methods to adapt closed LLMs privately using discrete prompts. Even on GPT-4 Turbo, the PICL performs poorly while incurring the highest cost. We showed that by using only Roberta Large and the private LoRa adaptation, we can obtain much higher accuracy of 89.3% at a much lower cost of only $3.85. Then the POPT requires Vicuna 7B and GPT-3 Da Vinci to obtain an average performance of only 81.4%. However, when adapting just Vicuna 7B using private LoRa, we outperform the POPT across the board. Here also we compare the cost, so the POPT is much more expensive when we compare it with private LoRa using to adapt Roberta Large. For the adaptation of private LoRa on Vicuna 7B, this adaptation requires a bit more fine-tuning, so then the cost can be a bit higher than for the POPT for these 10,000 queries. However, this cost amortizes for open LLMs with more queries. So if we send much more queries to Vicuna 7B adapted using private LoRa, then the very fast this open LLM case becomes much cheaper than adapting these closed LLMs. And finally, PROM-PATE plateaus very fast, but still we present here the result for epsilon equals 8, though after epsilon equals 0.3, PROM-PATE doesn't really improve. And this is because of limited number of prompts that we can actually include in the prompt template. Here we run PROM-PATE in this case Claude 2.1. PROM-PATE got the best result for this model. And here, even with the strongest method for closed LLMs adaptations, still we perform much worse than adapting open LLMs with private LoRa. Now let's compare open versus closed LLMs for the text generation tasks. We also analyze the private adaptations for text generation tasks, in this case being dialog summarization with Samsung. The cost here for the DPICL method on GPT-4 Turbo skyrockets to $3,500, and this is because we have many more tokens that actually are output from these queries using Samsung dataset. However, adapting OpenLlama 13b using our prompt Pate outperforms the DPICL at a much lower cost of less than $20. We further decrease the cost and increase the performance by using our PromptDPHD. So this is PromptDPHD on the BART large model. So here the cost can be reduced to as low as roughly $2. We can also boost the performance a little bit if we apply private LoRa instead of PromptDPHD on the same LLM, but also the cost slightly increases. And finally, we can leverage one of the top-notch OpenLLMs, in this case Mixtral 8x7b, to obtain highest performance. However, also at a substantial increase in the cost to around $68. So to summarize, we learned that we can perform an efficient adaptation of LLMs, for example with prompts. We can use either soft prompts, prefix tuning, or discrete prompts. Then we observed that LLM adaptations might leak private information about our sensitive data. We showed how to do it, for example, using the membership inference attacks. On the other hand, prompt Pate allows us to protect our private data for discrete prompts by leveraging an ensemble of private prompts and using the noisy argmax mechanism in the Pate framework. Finally, we showed how to also adapt with privacy the soft prompt and prefix tuning methods, and here we just leverage the PhD algorithm where we clip the gradients and add noise to the sum of the clipped gradients. Finally, we showed that the adaptations of OpenLLMs are in general more private, more performant, and much more cost effective than adaptations of closed LLMs. With that, I would like to thank you for